In this video, we're going to review derivatives of exponential functions. Here are the derivative rules. For natural base e or constant base positive b, here are the rules. The derivative of e to the x is e to the x. The derivative of b to the x is b to the x times natural log of b. Note that these are really just both the same rules. The rule for the natural base is a special case as the rule for the positive base. Because if we were to plug e equal to b into this rule, we would have e to the x times natural log of e, and natural log of e is just equal to 1, so it ends up being the same result as this one. Now, a lot of times exponential functions appear in applications with relative growth or decay. So if we're working on a problem of that nature and our growth or decay rate is k, then the derivative rule appears like this. This is done by applying the chain rule to e to the kx. Here, the outer function in the chain rule is the exponential, and the derivative of e to the kx is itself. In the chain rule, we multiply by the derivative of the inner function, and the derivative of kx is k, and that's how we get the constant multiplier k out front. Let's do an example. We want to find the instantaneous rate of change of the function y equals 3 to the x at x equal 2. Remember, the instantaneous rate of change is just going to be the derivative. So first, I'm going to calculate the derivative of this function. We saw on the previous slide that the derivative rule for a positive base b exponential is to take the base raised to your variable 3 to the x times the natural log of the base. Now we want this rate of change specifically at x equal 2, so we'll need to plug that in to our derivative. So 3 squared times natural log of 3. 3 squared is equal to 9, so we get 9 times natural log of 3, or if we work this out as a decimal, it comes out to be about 9.8875. Let's do another example. In this example, we'd like to find the tangent line to the curve y equals e to the negative 0.64t at t equals 3. Remember, the slope of the tangent line is given by the derivative. So the first thing we need to do here is calculate the derivative of our function. So this one has a decay rate of negative 0.64, so we will need to use that chain rule when we calculate the derivative. So the outer derivative is my exponential e to the negative 0.64t. And then I multiply by the derivative of the inner function, which is the derivative of the exponent, which is negative 0.64. Now we need to calculate several things at our point, which is t equal to 3. So we need to find out what our original function is at that point so that we have a point through which we can draw the tangent line. So we're going to plug 3 into my original function first and get e to the negative 0.64 times 3, which is the same thing as e to the negative 1.92. And that comes out to be about 0.1466. Now we'll also need to calculate the derivative at t equal 3. So here we're going to plug t equal 3 into the derivative, which looks like that. And when I put that into a calculator, it comes out to be about negative 0.0938. Now let's write the equation of the tangent line. I'm going to use point slope form, which tells me to take y minus the y value of the point, which is 0.1466. This should be equal to the slope of the line, which is my derivative value, 0.0938, times x minus the x value of the point, which is 3. And I used x and y here. The original problem used t. You could very easily plug in t for x as well if you wanted to express it that way. If you were trying to graph it in terms of the typical Cartesian plane, you would use x in this position and y in this position.